Okay, so today we're going to talk about limit at infinity. These are problems where x is approaching positive or negative infinity, and how to evaluate the actual limit of that particular function. Now, you've actually seen these before in your pre-calculus class. These are your horizontal asymptotes for your functions. Because remember, the horizontal asymptote is the number that the function approaches if we get really, really big, x is approaching positive infinity, or really, really small, x is approaching negative infinity. So how we handle these is very similar to how you handle the horizontal asymptotes for most of the problems. Now, the one property of infinite limits is as follows. The limit as x approaches infinity of some number c over x to an exponent will be 0. If we're dividing by infinity, x is in the denominator of a fraction, that is a particular expression equal to 0, which simplifies the entire problem. So if I have, like, for example, 1 over x minus 2, as x approaches infinity, this becomes 0. 0 minus 2 is just simply negative 2. So the whole goal for most of these functions, since they're rational functions, is to simply get in a way to create the c over x to the r property that we talked about. This allows us to deal with something very nice. Now, if the following answer is just a number over 0 or infinity over a number, then it still does not exist. That holds true still. We can't lose that property. But the whole key is to get problems where we have this right here, a number over a variable. That's the key for all these problems as the x approaches infinity. Again, if they're looking for something where it's simply a little more that does not exist, whether it's positive or negative infinity, exactly what we talked about last time, you want to either use your calculator to see what number we're approaching, positive or negative, or plug in this case, a very big or very big positive, very big negative number. The reason why it has to be big in this case, because we're talking about approaching positive infinity, I can't just plug in 2. It's not really big. I want to plug in like 5,000. That's bigger. Okay? So, first off, the limit as x approaches infinity of 4 plus 3 over x. Well, 4 plus 3 over infinity. Again, remember, if infinity is in the denominator, this goes to 0. So it becomes 4 plus 0, which is just simply 4. Very straightforward. So if the fraction is already there for us, life's very easy. If it's not already there for us, like in this particular example, what we need to do is we need to create them. So the key for these problems is we take a look at the variables we have. We have 2x minus 1, 3x plus 2. And I look for the highest power of that variable, which in this case is just x. There's no exponents for these. And what I'll do is I'll divide each piece of this expression by the highest variable. So I'll do 2x over x minus 1 over x, 3x over x plus 2 over x. This is nice because the x's will cancel for the 2 and the 3, but nothing will happen for the negative 1 and the positive 2. So I'll have 2 minus 1 over x over 3 plus 2 over x. And again, since x is approaching an infinity, anywhere we have x in the denominator, those go to 0. Leaving us just 2 minus 0 over 3 plus 0, which is just simply 2/3. Exactly how we want to handle the problem. Always, always, always divide by the highest power of x. That'll create fractions. Right? When the fractions left over will be 0. Anything that's not a fraction, because the x's cancel, will be the nice number you want to work with. In this case, it's 2/3. So, the limit as x approaches negative infinity of 5x squared over x plus 3. So in this particular case, the highest exponent is x squared. So I'm going to divide everything by x squared. The x squareds will cancel for the 5. I'll cancel one of the x's for the x, and nothing can cancel for the 3. Leaving just 5 over 1 over x plus 3 over x squared. Again, anywhere there is a variable, not variable, in the denominator here, it is now 0. And we have a does not exist case. So the question is this approaching a positive infinity or a negative infinity? So what we're going to want to do is we're going to plug in a really big number, but negative because we're approaching negative infinity. So let's plug in negative 1,000. So 5 times negative 1,000 squared over negative 1,000 plus 3. Well, negative 1,000 squared is going to come out to be 1 million. So 5 times 1 million is 5 million. Over a negative 997. Positive divided by negative is some negative number, negative something. Don't care. Doesn't matter. Because it's a negative number, this really means we're really approaching a negative infinity. Again, we're using a similar technique to what we just talked about in the last section, limits, infinite limits, to figure out whether or not we're positive or negative in this case. Again, negative infinity, that's why we plugged in a really big negative number. Didn't matter. I could have plugged in negative 1,000,000 and still gotten the same results. Still would have been positive up top, so it would have been negative on the bottom. Still would have been a negative infinity for my final answer. Now we got to be careful when we're dealing with square roots, because you need to be careful. It's going to be a little tricky because if you look at x squared is the highest exponent, I'll divide everything by x squared. But notice the x squared is inside a square root. So in reality, the biggest exponent, since x squared inside the square root, is really just x up top. So what we want to do is we're going to divide everything by x. So we have the square root of x squared minus 1 divided by x, and negative 2x over x plus 1 over x. But because it's a square root, I need to divide it nicer, so instead of dividing by x, I'll divide by the square root of x. That's equivalent. This will work out because the x's cancel. The x squareds will cancel, leaving just the square root of 1 minus 1 over x squared. And we have 1 over x over here. Again, anywhere where we have a x in the denominator, that will become 0. And just the square root of 1 over negative 2, which is a negative 1/2. So again, to recap, if you have a square root or a cube root or any kind of root, you can't assume the exponent inside is the actual highest exponent. You need to make it equivalent to just simply something without any roots. So I take the square root of x squared, that is just x. So the highest power up top is x, so is the bottom, that's why I'm dividing by x. Had this been an x squared, I would have to divide top and bottom by x squared. Meaning the top would be divided by the square root of x to the 4th, because it has to be equivalent to actually cancel it inside. Similar thing going on in this particular case. We want to divide top and bottom by the highest power, because we have the square root of x squared inside there. Similar thing, it's equivalent to x. So actually, let's just make this x squared right here. Change the problem a little bit. Because since the top highest power is x squared, the bottom high power is really x, we'll divide everything by x squared. So I have x squared divided by x squared. And on the bottom, we have our square root of x squared minus x divided by x squared. But again, if it's x squared, that's equivalent to square root of x to the 4th. So up top we just get 1. On the bottom we have the square root. X squared over x to the 4th is 1 over x squared. Negative x over x to the 4th is negative 1 over x cubed. Those both go to 0. We have 1 over 0. So it does not exist. So the key is, again, to plug in a really big negative number, like negative 1,000 again, and see what happens. So we get 1 million up top, divided by the square root of 1 million minus 1,000. Well, the key is this will be a positive number. Positive divided by positive is positive. So this is really a positive infinity answer. Okay? So that's how you're dealing with your different exponents. You got to be careful when you're dealing with square roots. Now, we have sine of 2x over x. This is another case where you have to be careful. And in this particular kind of problem, we're actually going to skip it for right now. This is not something you really want to deal with, because you can't really evaluate sine of infinity. That's an irrelevant answer. It doesn't exist. So what we want to talk about then, is we're going to talk about a different way of doing this one in a different kind of section. Actually, the next section we talk about is one we'll deal with for this kind of problem. So we'll hold off on this for right now. If you watch the next video in the series, L'Hopital's rule, and I think I pronounced that right, that will talk about how to actually evaluate this particular limit. Alright, in general, guidelines for finding limits at infinity for rational functions, if they're just rational functions. If the degree of the numerator is less than the degree of the denominator, the limit is equal to 0. If the degrees of top and bottom are equal to each other, the limit is the ratio of the leading coefficients. And if the degree of the numerator is greater, the limit does not exist, positive or negative infinity. This is the exact same rules you found for dealing with horizontal asymptotes. Now, if they're not rational functions, or stuff like this particular problem right here, you will use, like I said, you're going to use L'Hopital's rule instead. Okay, and we will talk about that. Alright, I will see you next time when we talk about L'Hopital's rule.